concept because that concept is being used by all those procedures to determine that target displacement, and that concept is called the concept of an equivalent single degree of freedom system. See, in the conventional pushover analysis procedure, we use a nonlinear computer model and we push it with some load pattern, right? And again, I will say that I'm skipping all that discussion about what are those types of this load pattern and what effect they have on the pushover curve. I'm skipping all that detail. Just want to give a quick overview. So we have a load pattern which is representing the pattern of future applied loading, and then we apply that pattern in a monotonic manner to develop that pushover curve. Up till now we know that. Now we can go further to convert that pushover curve into a force deformation curve, because this is roof displacement, this is the total base shear or a total base shear force. So we can idealize that curve in some simplified manner like straight lines and convert it into force deformation behavior, force versus deformation, and assign it as a input or behavior to a single degree of freedom system. So now if we convert this into force deformation, and then the stiffness of this single degree of freedom system is represented by this force deformation, then it is an equivalent single degree of freedom system which is representing that whole three-dimensional or two-dimensional nonlinear computer model. So this pushover curve of a structure multiple degree of freedom system can be mapped to a single degree of freedom system, and then that single degree may represent or may start representing the actual multiple degree of freedom system. This is called the concept of an equivalent single degree of freedom system. This concept is being used by several of the analysis procedures to determine that target displacement for pushover analysis. So I repeat again that the idea is that we can convert the pushover curve into in an idealized form as a force deformation behavior and give it as an input to our single degree of freedom system. So now that single degree of freedom system is not elastic anymore, because the conventional single degree of freedom system is governed by a mass and a constant K matrix and some damping ratios I. But now if we replace this K, which is a constant K, if we replace it with this curve, force versus deformation curve, which is nonlinear curve, which is telling us that up till some time the structure will remain linear, then it will become plastic, then it will go down from the ultimate point. So if we give this curve as the stiffness of this single degree of freedom system, now this single degree of freedom system becomes nonlinear. This single degree of freedom system will follow this line, dotted line, right? And since it will follow this line, and this line is coming from idealization of the pushover curve of a real multiple degree of freedom system, which means that this single degree of freedom system is now equivalent of that multiple degree of freedom system in behavior, right? So we give the same behavior to this single degree, and now it starts representing in a simplified manner that multiple degree of freedom system. So based on this this equivalent SDF concept, there are basically two types of methods which are there to calculate the target displacement. One is based on the idea of equivalent linearization. Equivalent linearization idea says that a nonlinear system can be approximately represented by an equivalent linear system with elongated time period and with additional damping. The second approach says that, which is called displacement modification, it simply says that the displacement of an elastic single degree of freedom system can be modified by some empirical factors to convert it into inelastic target displacement. So there are different methods which are listed here for each of the approach. The capacity spectrum method of ATC40, which was very widely used in the first generation of performance-based design, that was based on the idea of equivalent linearization. That we first develop our equivalent nonlinear single degree of freedom system and then convert it into an equivalent linear single degree of freedom system, and then we can uh, approximate or calculate the performance point or target displacement. Similarly, FEMA 440 developed an improved equivalent linear procedure in 2005. I'll not go into detail of these methods. The second approach says that you can simply take the displacement of a linear single degree of freedom system and then modify based on the properties of a nonlinear system. You modify that elastic displacement to calculate the target displacement. So there is a displacement coefficient method, and that method is still being used by ASCE 41, ASCE 41 06, 13 and then 17 also. The nonlinear static procedure prescribed in these documents is based on the displacement modification approach. So although we will not go into details of these methods, our target is to discuss the multi-mode pushover. But I want to just quickly show you in just one slide each of these methods. But before that, there is a third method also I want to highlight. So if this is first approach, this is second approach, there can be a third approach also, and that is that once we develop the nonlinear equivalent single degree of freedom system for our multiple degree model, we can simply perform the nonlinear time history analysis of that single degree of freedom system. We can simply shake that single degree of freedom system by the same earthquake against which we want to calculate the response, right? So we can shake that single degree and calculate the peak displacement U max, and that is actually equal to that XRIN, right? So again we estimate that XRIN from this method and go back to our pushover curve and stop the analysis at that particular step and extract all the responses. So again I go back to the same slide. So this XRIN we can also estimate from the time history analysis of an equivalent single degree of freedom system. And actually this is the idea which is used by several of the uh, approximate analysis procedures which use more than one vibration mode, because the idea is that we can use the modal inertia load pattern to convert it into an equivalent single degree of freedom system representing only that mode of the building, and we can do it for each vibration mode, and then we uh, perform multi-mode pushover analysis. This is the basic idea behind modal pushover analysis. So first approach, equivalent linearization, which says that we idealize this nonlinear single degree as an linear single degree with modified properties and then estimate the target displacement. Second idea says that we can start with the linear single degree of freedom system to estimate its peak displacement and then modify it based on our pushover properties to convert it into nonlinear. And third idea, I can write it here, nonlinear response history analysis of equivalent single degree. That instead of using any of the two simplified approaches, why not we directly apply the dynamic analysis procedure to our equivalent SDF system. Obviously, it will take a lot, significantly less time compared to the nonlinear time history analysis of the complete multiple degree of freedom system. So single degree will be solved in a matter of minute, and then you can estimate the XRIN from this, and again come back to your pushover analysis and extract all the responses when your roof displacement was equal to this XRIN, the maximum displacement produced by your ground shaking. Obviously, you have to first convert the maximum displacement of your single degree into roof displacement of your multiple degree, Actually, you have to multiply it with the modal participation factor, which I'll explain in the next slides. So the first method is based on the equivalent linearization. I just quickly give you an idea about capacity spectrum method. And the basic idea is that we convert our pushover curve into another form, which is called SASD form. The base shear is converted to spectral acceleration. The roof displacement is converted to spectral displacement. And this SASD form is called capacity spectrum. So here in the first step after the pushover analysis, we are converting our base shear and roof displacement into SA and SD respectively. Then the demand spectrum, which is actually the another form of the response spectrum of our curve, which is called ADRS form. Actually, it is spectral acceleration versus spectral displacement. This curve is called the demand spectrum, and it is representing the level of ground shaking actually. So it is simple response spectrum converted into spectral acceleration, spectral displacement form. The conversion expressions are available. This is the expression to convert spectral acceleration versus time period into SASD form. Similarly, these two expressions are to convert the base shear and roof displacement to the SASD form. But the demand spectrum should be reduced from the original spectrum based on the effective damping. Effective damping is actually the damping of the equivalent linear single degree of freedom system. Original inherent damping plus the additional hysteretic damping, which is estimated in ATC 40 by the bilinear idealization of that nonlinear single degree of freedom system. So we overlay these two curves, capacity spectrum and demand spectrum, both are in the SA versus SD form. We overlay on the same graph, and their intersection point is the compromise point between demand and capacity, and this displacement, roof displacement or SD, corresponding to their intersection is the target displacement. So you go back again to your pushover analysis and extract all the responses at this delta P or performance point. So this is one method to determine XRIM, that you overlay both the demand curve and the capacity curve on the same graph using the idea of equivalent linearization, idea of effective damping and secant time period, and then you calculate the performance point or target displacement. The second method is the displacement coefficient method, and that is based on the idea that we can simply start with the elastic displacement of our system. So this whole thing which I am encircling now is actually the elastic displacement, and this can come from the elastic response spectrum also for our single degree of freedom system or for first mode of our building. And then we can modify them with that elastic displacement with several coefficients C0, C1, C2, and C1 and C2 are the coefficients which account for different aspects of nonlinearity, and those C1 and C2 empirical coefficients are the function of the properties of pushover curve. So we idealize pushover curve with a bilinear approximation, and then the approximate yield point is calculated, and using that this RY factor is calculated, which is used in C1 and C2 expressions, and then they are used to modify the elastic displacement to get this delta T. Delta T is the target displacement. So once you get again that target displacement from that method, you again come back to pushover analysis and extract your responses corresponding to when your roof displacement was equal to delta T, right? So both of these approaches or methods, obviously there are refined methods also. There is a original displacement coefficient method in the ATC 40, just like capacity spectrum method, but then in 2005 FEMA 440 developed the improved versions of both the capacity spectrum method and the displacement coefficient methods, and that displacement coefficient method was later adopted by ASCE 41, in ASCE 41-06 and then 13 and now 17. So this displacement coefficient method, this one, is now being used in the ASCE 41 as the nonlinear static procedure. So the basic idea for all the pushover analysis is same, that you estimate the peak inelastic roof displacement using some method, approximate method, and push your building up till that point and then extract all the responses. Or if you push it for all the roof displacement, extract the responses only corresponding to that point, because those responses will be your approximate seismic responses. So later the same method was adopted by ASCE 41-13 and then 17 also, only this the notation is slightly different. Ry is now mu strength, otherwise the method is same. So it is the same displacement coefficient method as developed by FEMA 440. This is that third method which I was talking about, and that is that you directly perform the nonlinear time history analysis of that equivalent nonlinear single degree of freedom system. So you push your building, generate the pushover curve, give it as a force displacement relationship to your single degree of freedom system, and perform the dynamic analysis of that single degree of freedom system. The response of that single degree of freedom system, displacement response, you can pick the peak number, and that peak number can be converted into the peak roof displacement of your multiple degree of freedom system. Come back again to your pushover curve and extract all the responses at that peak displacement. So all three approaches are aiming at determining this peak roof displacement, right? But they are based on different assumptions. One important point is that when you give this monotonic curve or backbone curve to your equivalent single degree of freedom system, you also have to provide a cyclic behavior also. So you should tell the program which is modeling this single degree of freedom system, you have to tell what unloading or reloading rule should be used for that single degree of freedom system, right? So with this hysteretic rule and this dotted backbone curve, you can model that single degree, run that single degree in a matter of minute and directly extract the peak response. This is the idea which will be used for a procedure called uncoupled modal response history analysis, and it have few limitations and few approximations which we will be discussing next. Actually, these three methods differ based on different assumptions they invoke. So there can be some, you can say, difference in the predictions from these three methods, predictions of the target displacement or performance point, right? So based on the relative accuracy, you may get a different number for performance point from any of these three methods. But that number can be anywhere on the pushover curve, obviously, because what you will be calculating is the XRIN, right, in each case. So corresponding to that XRIN, you can pick the base shear, and actually in the analysis program you just have to provide this XRIN because, for example, let's say that you perform up till 50 inches with each increment of 1 inches, right? And your calculated XRIN is, let's say, 32 inches, right? So what you will do is that you will directly go to the 32nd analysis step, and all the analysis results at that particular step actually are your seismic responses, right? Or if you can estimate that 32 inches in the start of that process, you can only push your building up till 32 inches. No need to go beyond that, right? But it is generally recommended to go beyond that to see what will happen if the peak inelastic roof displacement is exceeded in the future earthquake, right? So it is always recommended to get a full picture first and then estimate the you can say peak inelastic roof displacement. Actually, some of the methods, actually in fact all of the methods require the properties of this pushover curve to calculate this XRIN. Because for example in the displacement coefficient method you need to have a bilinear idealization of this curve. So you have to have this full curve first in order to calculate this XRI. Similarly, you don't know in this particular third method, which I am discussing in this particular slide, you don't know that what will be the XRIN before performing the time history analysis. So it is always recommended to get the full curve first up till the complete failure, for example, or significant failure, and then idealize it with a forced deformation curve and then perform the analysis to see what displacement is caused by the future earthquake, right? So based on the relative accuracy of these three methods, you may get a slightly different estimate of peak roof displacement or target displacement or performance point.